So we're talking about biasing diodes, and I want to answer a few questions here. First of all, explain how to prevent a transistor from going into cutoff or saturation when an input signal is applied. And this happens with the biasing. So with your biasing circuit, you want to make sure that your Q point is near the center of your load line. Remember, when you're looking at your biasing circuit and you've got your VCE and your collector current here, your load line is going to be where cutoff occurs at your VCC. So if that's 10 volts, that'll be your end point of the load line. And then your IC will be your IC saturation, which is when your transistor looks like a short circuit. And so what you want to do is, when you draw your load line, try to stay with your design, try to stay somewhere in the middle for that Q point, and that way when you introduce your sinusoidal waveform about that point, you'll stay somewhat in the same area without cutting off without cutting off your waveform or distorting it in some way. Okay, let's work some problems now. So here we have so for a base bias here, so base bias, so we don't have any resistor at the emitter. We don't have a voltage divider at the base, so it's just a base bias here. So if we have IB is 150 microamps and the beta is 75, the voltage at C, remember that's right here, that's your collector, that's your base, and that's your emitter. And then our RC is 1K right here. What is the Q point? Okay, so remember, the Q point is defined as your VCE and your collector current. So the first thing is, we know that the collector current is the beta times IB, and we were given both of those. So we've got 75, which is the ratio of the collector current to the base current, and that's 150 microamps. Okay, so that should give us about 11.25 milliamps for our IC. And then VC is going to be whatever your VCC is. Actually, did I write that one wrong? Let me go back to where that's drawn. Number 4, VCC is 18, that's right. Just making sure. VCC minus whatever the voltage drop is across RC, which is going to be IC times RC. That's our Ohm's law relationship there. So we're applying 18 volts VCC minus the 11.25 milliamps that we just found, which is 75 times the base current, times the 1 kilo ohm of resistance that we have at the collector. Okay. So that should give us about 6.75 volts at C. Now VCE is VC minus VE. So, and at VE here, VE is actually connected to ground. So that's going to be our 6.75 volts we have at the collector minus 0 volts at the emitter, which would just be 6.7 volts. And so our operating point would be at the 6.7 volts and 11.25 milliamps for that problem. Okay, so for number 8, what should our input voltage be at the base in order to give us that 20 microamps at the base if the beta is 50? Okay, so let's look at a couple things here. First of all, we know that we need to have a drop of 0.7 volts from the base to the emitter. Okay, again, base, emitter, collector. Just to remind you, the side with the arrow is always going to be the emitter. The base is going into this base, what looks kind of like a base to the device itself, and then the collector will be opposite the emitter. All right, and then VE is at 0 volts because it's connected here at ground. Okay, so what we want to measure, VB should be VE plus 0.7 volts, and if VE is 0, that means VB needs to be 0.7 volts. Okay, so we need a voltage drop across RB that will give us that 20 microamps. So we can use Ohm's law to figure that out. We know that we have IB times RB, and that would give us that voltage drop. So if we want that to be 20 microamps, and we want 1 mega ohm of resistance there, that means we would need a 20 volt drop across RB. So if we have a 0.7 volt drop here, and we have a 20 volt drop here, we have to have at least 20.7 volts applied. So the answer to that would be 20.7 volts applied at VBB. Now we're also asked to find IC and VCE. IC again is just the beta times IB. So if we have a beta of 50 times the 20 microamps, which would be about 1 milliamp. And then VCE would be whatever the voltage at the collector is minus VE, and we know that VE is 0, so it's really just going to be VC. And we get that by taking our VCC that we're applying and subtracting whatever the voltage drop is across RC. So that's going to be IC times RC. That's using our Ohm's law relationship there. So we have 20 minus the 1 milliamp times 10K, which should be about 10 volts. All right. Okay, so for the next problem, we're trying to figure out if this transistor is biased in the cutoff region, the saturation region, or the linear region. Okay, so first of all, if it's in cutoff, that means that we don't have enough current into the base to turn it on. And you can kind of tell that by, do you have at least 0.7 volts that is going to allow you to bias that base to emitter region in the forward direction. And we are supplying 1.5, so it's a pretty good chance that we have at least enough voltage drop across RB to turn that on. Because what we would have was we would have 1.5 volts minus the 0.7 would give us the 0.8 volts drop across RB. So if the voltage drop across RB is 0.8 volts, that would mean that IB would be the 0.8 volts divided by the 10 kiloohms. Okay, so 0.8 divided by 10K would give us about 80 microamps. And that should be enough, of course, to turn on our transistor. So I don't think it's in the cutoff region. What we do want to make sure is that when we multiply this by the beta, that doesn't put us into saturation. So let's just look at what IC would be if it's in the linear region. So that's going to be beta times IB, where we have 75 times 80 microamps. And that means that we would have about 6 milliamps there. Now, what is the IC sat? We need to figure out what IC the saturation would be. And that's going to be when our transistor is looking like a short circuit from the collector to the emitter. So that would be basically an 8-volt drop to ground divided by whatever resistance is in that path. So we only have the resistance of at the collector. So 8 divided by 390 will give us whatever that maximum current is we could have, which was about 20.5 milliamps. That is our saturation current. That is the greatest current we'd expect to see, and at that point we're in saturation. So IC is much smaller than IC sat. So that tells me that we are operating in the linear region. Okay, so basically we figured out that we have enough voltage to turn on the transistor, and we have a low enough current that we're not going to actually put the transistor in saturation. So that's why we're in linear, operating in the linear mode. Okay, let's determine the transistor terminal voltages with respect to ground. So what that means is, here at our collector, VC, here at our base, VB, here at our emitter, VE, we're just going to measure each of those with respect to ground. So when we say with respect to ground, what that means is we're going to take our voltmeter and connect the red lead to that point, and then connect the black lead to ground. And that's what it means to measure with respect to ground. Your black lead is at ground, and you're just measuring on the positive side the other point in the circuit that you want to measure. Okay, so let's look at first we have a voltage divider bias. So what that tells me is that we can either use the approximate method or the exact method to come up with our VB. So we need to figure out which we can use. So if the beta times RE is greater than or equal to 10 times R2, we can use the approximate method. And I'll show you that in just a minute. So let's do our check here. So the beta is 110, and we have a 1K ohm resistor at the emitter, and then 10 times the 15K. So that is, we've got 110K over here, greater than or equal to 150K. So that's a no. Okay. Now we could still do it. It would just be a little further away from the actual values that we're looking for. So we're going to use the exact method, which is our Thevenin method. Okay, so to do this, we're finding E Thevenin and R Thevenin. And you can just use equations for this. Essentially what Thevenin's equivalent circuit means is that we're going to take our circuit from the base to the emitter, and we're gonna consolidate that and find the equivalent voltage source and resistor that would be in series with that in order to give us the same voltage and the same current there. So I'll just give you equations to do that. So the R Thevenin would be the R1 in parallel with R2. Now, you know how to combine parallel resistors. It would be 1 over R1 plus 1 over R2. However, since we've only got 2 resistors, we can also use the product over the sum to get that as well. And it's a little easier to remember. So that would be 47K times 15K over 47K plus 15K. And so let's work that out. Should be about 11.4 kilo ohms. Okay, just remember when you're combining parallel resistors, the final result should always be smaller than the smallest resistor. So that would have to be less than 15K if we did this right. Next, we want to find our E Thevenin. Now, E Thevenin, all we need to do is find the voltage drop across R2. And we're going to use the voltage divider rule for that. So that's going to be R2 over R1 plus R2 times whatever that total voltage is, which is the 9 volts that we've applied at VCC. So we've got 47K over 47, oh, I did that wrong, not 47K, it's the 15K that we want on the top because that's the voltage we're looking at, plus 15K over here times 9. And so when we figure that out, we get 2.18 volts there. And that will be our E Thevenin. All right. So what does that mean when we find the Thevenin equivalent circuit? That means that we're going to have a VBB over here that is our E Thevenin. That is going to be 2.18 volts. And then in series with that is going to be our R Thevenin, which was the 11.4 kilo ohms. And then we're just going to keep the rest of our circuit over here. So here's the 9 volts that we applied before. Here is the 2.2K ohm resistor here. And then, of course, we have RE, which is 1 kilo ohm. And so what we do when we use the exact method, we are simply replacing our voltage divider over here with something that's a little easier for us to work with and gives us a little more exact numbers. Okay, so now we want to find all of our voltages with respect to ground. So how are we going to do this? Well, first of all, remember that you're going to have your 0.7 volt drop here. Okay. Now, you can just use the equation that you're given in the book. I actually like to go back and look at the KVL for this loop here. So the KVL equation would be, first of all, since you're starting at ground and we're going in this clockwise direction, we're going to see a rise of 2.18 volts minus whatever the voltage drop is across that R Thevenin. I'm just going to say I don't know what it is right now. Minus the 0.7 volt drop you have here from the base to the emitter. Don't forget that. And then minus whatever the voltage drop is across RE. That gets us back to ground. So that would have to be 0. Now, the voltage drop across R Thevenin is going to be your base current times whatever that resistance is. So I'm going to substitute this into the equation for that voltage. And then the voltage at across the emitter resistor, that's going to be the emitter resistor times the current through it, which would be IE, right? However, we know that IE is equal to IC plus IB. And we also know that IC is equal to beta times IB. So if we combine those two things, we see that IE is beta IB plus IB. And if I pull IB out of there, that would be beta plus 1. So I'm just going to use that. We could just assume that IC and IE are pretty much the same and just use beta IB, and that would be fine. However, if you want to be a little more exact about it, I'm just going to say that VRE is beta plus 1 times IB. Let me get a little more room here. Beta plus 1 IB times RE. And I'm going to substitute this into here. So what that does is I can then solve for IB because that's going to be the only unknown that I have. And you can work with this a little bit on your own if you want, but IB times R Thevenin, 11.4K, minus 0.7, minus beta plus 1, which is 111, IB times 1K, and that all has to equal 0. So IB would be the 2.18 minus 0.7 over 11.4K plus 111 times 1K, And I know the math is a little bit, looks a little challenging there, but it's really not if you just kind of work back through it. Okay, so it looks like to me that IB should be about 12.09 microamps. And that's going to allow us to find all of our voltages. So if we have 12.09 microamps at B, then the voltage at B would be the 2.18 volts that we are supplying at VBB minus 11.4 K times 12.09 microamps. Which gives us about 2.04 volts at VB. VE, of course, is going to be VB minus the 0.7. So I'm just going to subtract 0.7 from that. Again, this is an approximation. So about 1.34 volts for VE and VB. And then for VC, we need the VCC minus IC times RC. So we're going to need IC, and IC is beta times IB. So we've got 110 times the 12.09 microamps. Which is about 1.33 milliamps. So VC would be 9 volts minus 1.33 milliamps times 2.2 K ohms. Should be about 6.07. Okay, and there's your VC. Let's see, I think that's what we were asked for that problem. Okay. Now for the next few problems, we're going to work the same, work with the same circuit for all of these. Okay, so first of all, we're looking for VB. And again, we want to figure out, do we need to use the exact approach or the approximate approach? So we can use the approximate method if beta times RE is greater than or equal to 10 times R2, where R2 is this resistor on the bottom side of that voltage divider. So if beta is 150 and RE is 560, 10 times R2, so 150 times 560 is about 84K, and 10 times R2 is 56K. So yes, we could use the approximate method here. And I actually might do that. I think if you're looking at the textbook, I think the answers they use are for the exact approach. But since we used the exact approach before, let's do the approximate method now. It should be close enough for us to work with. Okay. However, oh, well, we first need to find VB. So if we use the approximation then VB would just be the voltage across R2 of our voltage divider. So we would use our voltage divider equation, the same one that we used to find E Thevenin in the previous problem. But now this is going to give us our VB and not just our V Thevenin times VCC. So we've got 5.6K over 33K plus 5.6K times the negative 12 volts. So that should be negative 1.74. Now, the question in part B is, if we change the beta to 50, what does that do to VB? Well, theoretically, it's going to make a little bit of a difference, but where it really makes the difference is in figuring out if we can use the approximate method or or if we have to use the exact method. So let's just look at this. If beta is now 50, then let's look at beta RE greater than or equal to 10 R2 and see if that works out. So 50 times 560 greater than or equal to 10 times 5.6K. Let's see what 50 times 560 is, and it's 28K. Greater than or equal to 56K? No. So that would mean we would need to use the exact method. So if I did that, my E Thevenin would be the negative 1.74 I found before, and my R Thevenin, of course, would be the R1, R2 over R1 plus. So I'm just going to go ahead and do that really quickly too. So we've got 33K times 5.6 divided by 38.6K. So that would be about 4.79K. Now, from the equation that I found before, our IB would be the negative 1.74, this time plus 0.7. Why that is because this is a PNP transistor, and so the drop of 0.7 would occur in the other direction because the emitter current is coming in and the base current is leaving in terms of conventional current. Okay, and that's going to be divided by the beta plus 1 times RE, or 560, plus the R Thevenin, 4.79K. So let's find our RB first. And that should be about 11.6 microamps. So VB would be the E Thevenin plus the drop across R Thevenin, which would be the 11.6 micro times the 4.79K. And let's see what that would make. That so it would be about 1.68 volts, negative 1.68. So would it change it? A little bit, yes, but not a lot. I mean, we're still looking at like 5 to 6 millivolts, or actually 50 to 60 millivolts. So a very small amount of voltage. It would make a difference, but not a big difference. Okay, so what are the Q point values? Now, since we're going back to this beta of 150, I'm going to go ahead and stick with the approximate method where we're just going to assume that we have a negative 1.74 volts here. And then that means that here we would have the negative 1.74 plus 0.7, so negative 1.04 volts here. So if we're looking for our current, we have 0 volts on this side and negative 1.04 volts on the other side. So our current here would be negative 1.04 over 560 ohms. Or about 1.86 milliamps. And just for good measure, let's just go ahead and assume that IC is approximately equal to IE. We're just going to do this approximation this time and see how it works for us. So let's just assume we also have 1.86 milliamps here. We do know that it's going to be a little bit smaller than what IE is, but again, let's just do our approximation. So if that's the case, we can determine what our voltage drop would be across RC, because that voltage drop is going to be the 1.86 milliamps times the 1.8K. And that gives us a drop of about 3.34 volts. 3.34 volts here. Okay, so if we have a negative 12 here, and then we see this basically a voltage rise of 3.3 volts, that means that on the other side we should have 8.66 volts. So I'm going to keep that in green. So about 8.66 volts here. Actually negative, because we've started at a negative 12 here, and we've added 3.34 volts. So we're still at negative. So our VB right now, we've got 1.74 volts. VC, we've got negative 8.66 volts. VE, we're at negative 1.04 volts. So our VCE, again, would be VC minus VE, which is going to be a plus because we're subtracting a negative number there. So we're going to see a drop of 7.61 volts drop. Actually, it's going to be a voltage rise from the collector to the emitter. So we're going to say 7.61 there. And the IC, of course, we just said was, we're going to estimate it to be the same as IE, or about 1.86 milliamps. Okay. And the minimum power rating. So let me just write these down. So the Q point values are VCE is 7.61 volts. And okay, actually, let me look at this a little bit more. So we're going to see a voltage rise here of 7.61 volts. That's right. Okay, so we're just going to stick with, it should be negative. Okay, it should be negative because VC, oh, I think I left off a number there, negative 7.1. Okay, so negative 7.61 IC is at 1.86 milliamps. And then the power rating. The power rating is going to be the VCE times IC. So 7.61, and that's volts, 1.86 milliamps. Means about 14.17 milliwatts. Let me see, 1.86 milliamps times 7.61. Yeah, about 14.1 milliwatts. And then for 20, I1, I2, and IB. So IB we already found. So I determined that IB needed to be about 11.6 microamps. Now I1 and I2. When we do this approximate method, we're assuming that I1 equals I2 because, and it will, I'll show you how this works out. So basically what we're going to do is start with 12 volts up here, and we've got the 1.74 here. So we should see a difference of 10.26 across the 33 k ohm resistor. So I'm just going to 12 minus 1.74 over the 33K will give us about 311 microamps. Now I2 is going to be about the same thing because it's going to be this 1.74 minus 0 over 5.6K. 1.74 minus 0 over 5.6K. And the assumption I made was that I1 equals I2. That's how I got the results that I had already. Which should be about the same thing. So it is going to give me about 311 microamps. Now, if we had used the exact method, we would find something slightly different because we would have a different IB. But in this case, the approximate method assumes I1 equals I2, and that is what we found out because we used the approximate method. So we're just going to leave it at that. Okay. Okay, based on the measurements, are there any failures in the next few circuits? And if so, what might be the problem? So the first, we're just going to do a quick look at these and say, all right, so here we're measuring 0.7 at B, at the base, and about 10 millivolts at the emitter. So that tells us that we do have a drop of 0.7 here. So that's working correctly. Now, what does cause me some concern is we've got 12 volts at VCC, the voltage we're applying, and then we've got 12 volts at VC. So we see that we have no voltage drop across RC, which tells me that we don't have current there. So I would make an assumption that the collector is open for that one. So that's what I would think is the collector. We'd have an open circuit here at the collector, because the rest of the transistor looks like it's working properly. Okay, so for B, again, we've got 1.82 volts at the base. We've got 1.12 volts at the emitter. So that tells me that, yeah, we're probably okay there, because there's a 0.7 volt difference there. I can see that. Also, what I would look at is, what would the current be here? It would be 1.12 divided by 1K, or 1.12 milliamps. Well, what is the current here if we're measuring 8.8 on this side and 20 volts on this side? That would be 20 minus the 8.8 over 10K. So what would that give us? That's 20 minus 8.8 divided by 10K. And we get about 1.12 milliamps there as well. So, you know, since IC and IE are pretty much equal, I mean, they are equal, and we do have the 0.7 volt drop here, I'm inclined to believe that this is working. Okay, I don't see any problems with that. Now you could go dig a little deeper and try to find what the actual values ought to be, but since IC and IE are pretty much the same and you've got that 0.7 volt drop, I'm not concerned about that transistor. So let's see what we've got here. Oh, I can already see a problem here. So we do see that we have a 0.7 volt drop from the base to the emitter. Okay, so 0.7. However, we also see now that we have the same voltage at the collector that we do the emitter. So there's no voltage drop. So VCE is equal to 0. And that's concerning, because we do have enough current to turn on the transistor. So we should not be in the cutoff region, or in the saturation region. So that tells me that we probably have a short from the collector to the emitter. Okay, so there should be a voltage drop there somewhere. And then finally, okay, we've got almost 7 volts at the base, and we have 0 volts at the emitter, where we should have about 0.7. Looks like we have about 7 volts instead. So that tells me there's a problem there. Also, this we've got 9 volts at VCC and 9 volts on the other side of our resistor at the collector. So that tells me that there's no current here, because if there was a current through there, there would be a voltage drop of some sort, even if it's small. Since there's no voltage drop at all, that tells me there's no current, and no current and not a voltage drop here tells me that the emitter might be open. Okay, so that's probably what I would think. Okay, so those are just some problems working with the